Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Applications of Integration to the Normal Distribution. And as always, I encourage you to be an active learner as you watch this video. We will talk about the expected value, or also known as the mean. We'll talk about the variance, the expected value of x squared, the mean, the variance, and the standard deviation. We will use normal distribution tables to calculate normal distribution probabilities, and we'll also calculate percentiles for a normal distribution. Okay, suppose we have a uniform distribution where it is always f of x is equal to 1/3 over an interval of length. That's f of x equal 1/2 over an interval of length 2, where everything is equal probability. Then what we're going to do is to calculate the average of a bunch of sample numbers picked from this range. We would just take x1, x2, and 100 samples, divide by 100, and we would get this as our expression. Now, if we picked n that were uniformly distributed, we would get this expression, or rearranging it, it's doing this. Now we're multiplying really by 1 in a clever way because we're multiplying, dividing by 2. But you see, that gives us, since the interval width is 2 and the height of the rectangles is 2, that this actually is a Riemann sum. If we take the limit as this goes to infinity, we would get the integral from 3 to 5 of x times f of x dx. That motivates the definition of the expected value of x. So let x be a continuous random variable over the closed interval ab with probability density function lowercase f. The expected value of x then is defined to be e of x is equal to the definite integral from a to b of x times f of x dx. The concept of the expected value of a random variable can be generalized to functions of the random variable. Suppose that y is equal to g of x is a function of the random variable x. Then we have the following. The expected value of g of x is defined by the expected value of g of x is equal to the definite integral from a to b, and instead of putting x in there, we put g of x in there, times f of x dx, where f is the probability density function for x. Let's do an example. So here we're going to be taking this density function. That means that's greater than or equal to 0 on this interval, and if you integrate just the density function itself, it's equal to 1, and we're to find the expected value and the expected value of x squared. So e of x is going to be equal to, we just take x times the density function and integrate it from 4 to 6 dx. Now we do algebra first. That's the easiest way to do this. So we distribute this through. We get this. We pull the constants through the integral, and for each of these powers of x, we add 1 to the exponent and divide by the new exponent, and use the fundamental theorem to evaluate this integral, and with 16 over 3. Now if we wanted to find the expected value of x squared, we would, instead of putting x here, we're going to put x squared here. We would distribute and do algebra to start with, and we'll get this. We'll pull the constants through these definite integrals, add 1 to the exponents, divide by the new exponents, and use the fundamental theorem of calculus to calculate this. We'll get 86 over 3. Make sure that you are duplicating and understand these calculations. These are the kind of calculations I would ask you on an assessment. We now define the mean, mu. This is the Greek letter mu, that is an m, of a continuous random variable x, then is defined to be e of x. So mu is e of x. It's easier to write mu than e of x, that's why we do it. So mu then is going to also be the same as the expected value of x, which we learned before is the definite integral from a to b of x times f of x dx. And mu is, like we said, pronounced mu. We can get a physical idea of a mean of a random variable by pasting the graph of the probability density function on cardboard and cutting out the area under the curve over the interval AB. If we can find a balance point on the x-axis, so you see this is balanced, it's neither tilting this way nor this way, and here it's balanced differently, neither tilting this way nor this way, it's flat, then that is the mean. Mu is the value at which between A and B that we can find that balance. We're also concerned about variability, and for those measures we have the idea of the variance and the standard deviation. Because two different distributions can have the same mean, it's useful to have a second statistic that serves as a measure of how the data in a distribution is spread out, actually. Statistics that provide such a measure are the variance and especially the standard deviation of a distribution. You're going to see that these two are very similar, but the standard deviation will have the same units as the other statistics in the problem, like the mean. So if mu is the mean of a distribution, then x minus mu represents the deviation of a value x from the mean. The variance is the mean of the square of these deviations, or this. The reason we're squaring it is so plus variations do not cancel out with negative variations. So the variance, sigma squared, and that's the sigma that we talked about before for standard deviations, of a continuous random variable x defined on AB with probability density function lowercase f is sigma squared is equal to the expected value of x minus mu whole squared. And if you do the calculation and do the algebra, that's the same thing as the expected value of x squared minus mu squared, which is this. So it's this integral minus this integral squared. The standard deviation, sigma, of a continuous random variable is defined as sigma is the square root of the variance. And that is the lowercase Greek letter sigma. So let's do that for our favorite probability distribution that we had in the first two examples. We want to find the mean, variance, and the standard deviation. Now, we really already found the mean and e of x squared from the first two examples. So the mean, using our formula, is just going to be the expected value of x squared minus the expected value of x. We calculate that using the numbers we calculated before, and we conclude that this answer is, here, looks like it is 2/9. And the standard deviation is the square root of that. Now the square root of 9 is 3, but that is going to be the square root of 2/3. If you put that into a calculator, you will get this. The standard deviation is a measure of the spread of the data. That is, how far are the data points on average from a line x equal mu. So x equal mu is here. This is going to have a larger sigma because these are more spread out. This is going to have a smaller sigma because these are tightly bunched together. We're now going to turn our attention to a distribution called the normal distribution. That is the bell-shaped curve that you've often heard about. So suppose the average speed of cars is 70 miles per hour. Now many cars are going above it and many cars are going below it. And very few cars are actually traveling at that speed. And on a highway, the speeds are normally distributed, and that means this function, which does make the bell-shaped curve, is g of x is equal to e to the minus x squared over 2. It runs from minus infinity to positive infinity, but you see these get very close to 0 in the tails. And you could plug this into a calculator to find the values of this density function. And we're going to use this because that's going to be the normal distribution, and we're going to do a couple of things. In our book, we will find that there is a normal distribution for the mean of 0 and a standard deviation of 1. That's what is shown over here. And we'll talk about that table quite a bit. But also, in many of the word problems, we'll be talking about normal distributions, mean of mu, and standard deviation of sigma, where mu is not 0 and sigma is not 1. Now, it is good, though, that this is x space, so the variable over here will be x. This will be z space, because the variable here will be z. And they are connected by an area-preserving mapping called the z-score. That is, z is equal to x minus mu over sigma. And so you see that allows us to change from x space to z space. And we're going to be answering two great kind of questions. One is, given x, find p of x, the probability of x, and the other is, given p of x, find f of x. And we're going to be using this table sum. That's a little bit of a look ahead. But now let's return to the discussion of the normal distribution then. It can be shown that the improper integral is the area under the curve over minus infinity to infinity. And so if we did that, we would get the square root of 2 pi. Now, we don't know how to do this integral yet in this class, but trust me, we get that. And to build a table, you can do numerical integration to get numerical values for that. That's what's in the table. Now, note that this area is not 1, but if we divide by 1 over 2, the square root of 2 pi, we do get a density function. So here's our definition. A continuous random variable has a standard normal distribution if its probability density is this. You see this is always greater than or equal to 0 as we saw, and the integral is equal to 1. So that is a probability distribution function. And in general, if we shift it, and you see if the mean shifts, we shift it right or left, and we can also change the how tightly things are bunched. So the general distribution, this is the one whose numbers are in the back of your book. It has a mean of 0 and a standard deviation of 1. Here's the general case. A continuous random variable is normally distributed with mean mu and standard deviation sigma if its probability density function is given by this. Notice that what we do is we shift the x by mu and we scale it by sigma this way. And here are examples of shifting both mu and sigma. And of course you can shift both. The normal distribution is important in statistics. It underlies research in the natural, behavioral, and social sciences. Because of this, tables of approximate values of the definite integral using approximation techniques like we talked about, the trapezoidal rule, and these are in an appendix of your book, and we will provide this on tests as part of the grace notes, and present such a table. And so what happens is that in the table will show you the probability that x is between 0 and z, and that's going to be the definite integral from 0 to z of 1 over the square root of 2 pi e to the minus x squared dx. These are the table values that you'll see. We'll look at the table again. And the symmetry of the graph about the mean allows us to many types of probabilities can be computed from this table, and some involve addition and subtraction of different areas. Now, here's an important kind of consideration. If you say how much of the area is between minus sigma and sigma, you see that it is approximately equal to 68%. And so that means that 68% of the data is within one standard deviation of the mean. Similarly, 95% of the area, 95% of the data is between two standard deviations below and above the mean. And if you go 3 standard deviations, you capture over 99% of the data. This is sometimes called the 68, 95, 99 rule. And so in a standard normal distribution, 68% of the data is within one standard deviation, 95 is within 2, and 99 is within 3 standard deviations of the mean. And this is true not only in the normal 0, 1, it's true about any normal distribution. Okay, let's do some examples, and that means we want to look at the table just for a bit. Now this picture shows you what area is shown in the table, and the areas are the numbers that are in the body of the table. And these are the standard deviations. So we're going from 0 to whatever value of z I have. Now these are the first two significant digits going down this way, and the third significant digit is across here. So let's use this table that's in the back of your book and will be in your grace notes to calculate some things. So we're going to talk about what is the probability that x is between, x is normally distributed, so what's the probability that it's between 0 and 1.68? Well, we locate 1.68 in our table. This is where the 8 is. This is 1.68, and we get that number. And so that's the area that we're seeking, and you can see from the table that is 0.4535, and we got it from the table that way. We can also talk about calculating this one. We go from minus 0.97 up to 0. But this area is the same as this area with 0.97. So we go down to 0.9 and across to 0.7, and we get that number, and that tells us that this area is exactly that number. In this problem, we're trying to find the probability of this normally distributed x, where x goes from minus 2.43 to 1.1. But you see that's this part and this part. So here I'm going to calculate what is the area between 0 and 2.43. And I do that, and I get this number. But then I have to add it to the area that I get for 1.01. Here is 1.01 from our table. I add those areas together, and I get 0.8363. So here I want to find the area between 0.9 and 1.74. Now this is different. I'm going to find what is the area between 0 and 1.74 from the table. So let's look at 1.74, and we can see that that is going to be this 0.4591. And then I'm going to say what is the area going from 0 up to 0.9. And that is going to be, we will go up here to 0.9, and we will see that it is this number. It is 0.31. Let's see, that is going to be, yes, 0.3159. And so we subtract those two areas to get the net area we want, and this is 0.1432. Make sure you understand these examples because we're doing some clever things. If we want to go from minus 1.98 to minus 4.2, we're going to be subtracting the same way, but we're going to use the symmetry. So this is going to be the area from 0 to 1.98. If we look over here, 1.98 is going to be up here. It's this number. It is 0.4761. And then we're going to subtract off the area at 0.42, which is down here, which is 0.1623. We subtract the two, and we get this as our final answer. Last, but very importantly, we can also talk about the probability of x being greater than 0.61. Now I know this entire area from 0 to infinity is a half because of the symmetry, and so if I subtract off, so this is 0.5, but if I subtract off this area, 0.61, which again I can get from my table, it is here 0.2291, then I subtract the two areas and I find the area that I wanted. Make sure you understand these examples. They are not difficult, but require some practice. And for most normal distributions, mu does not equal 0 and sigma does not equal to 1, so we use the z transform like we talked about before. This basically turns it into how many standard deviations are we away from the mean, and that standardizes the distribution, and that means we can apply Appendix D and convert back. Such converted x values are called z-scores or z-values. And so the probability that x is between a and b is the probability that z, using that transformation, is between this number and this number. And this last probability can be found using Appendix D. Okay, so let's do an example of this. Suppose the weights of members of a cross-country track team are normally distributed with a mean of 150 pounds and a standard deviation of 25 pounds. Find the probability that the weight of the student on the team is between 160 and 180. Okay, so you see these are in X space. So what I'm going to do is I'm going to standardize these. So 160 is standardized to 0.4, and 180 is standardized to 1.2. Again, this is the value minus mu divided by sigma. So this area is equal to this area. Well, we can find this area from our normal tables. This is this area minus that area. Going to Appendix D, we subtract and we get this is the answer. And this was an area preserving map. So the probability that the weight of a randomly selected member of the team is 160 to 180 pounds is 0.2295, and that's about 23%. That was one great problem. There we were taking x and we were finding the probability of x. Now what we're going to do is we're going to know about the probability, and then we're going to determine what value. So this is going to be what is p of x, and we're to find x. And these are often called percentiles. Suppose you take an exam and score better than 85% of all the students taking the exam. We say that your score is in the 85th percentile. That means 85% scored below your score and 15% scored above. For the normal standard distribution, the percentile of each z value is the area under the standard normal curve to the left of z multiplied by 100. So if this were the z value, it's the area to the left of z multiplied by 100. Realize that your table only gives you this piece, so you have to add the 0.5 if z were like this. All right, so we're going to look at the standard normal with mu equals 0 and sigma equal 1 and determine the percentile corresponding to each of the following z values. Well, this is the mean, so that percentile is going to be 0.5 or 50%. This is z is 2.25. If I look that up, though, what I will find is this is 0.5, and I'll look at under 2.25, and I'll find that the percentile is 2.25. So that is going to be 0.4678. When I add the two together, I get this. So it's a 98.78th percentile. And last here I get z is 1.75, but I'm looking for this percentile. This is less than that. So I'm going to be subtracting this area from 1. So I look up by symmetry 1.75. I get this number. I add 0.5 to it, and then I subtract that from 1 to get this number. So that is the 4th percentile. Make sure you understand these calculations. Now let's do a real-world problem. A large chemistry class takes an exam, and the scores are normally distributed. The mean is 72, and the standard deviation is 9.1. The professor gives any student scoring the top percent an A. What is the minimum score needed to get an A? Okay, so we're really trying to figure out what's the top 10%. Now the top 10% means that this area should be this area. We're going to have 0.5 here, and this is 0.4. So we're going to look up and we'll find out what z value is here. We find that z is equal to 1.28. But now what we're going to do is we're going to use the z-score backwards. You see, here's the z-score. So 1.28 is equal to x minus 72 divided by 91. I solve this equation for x. I multiply both sides by 9.1, and then I add 72. So this is that score in X space. And so you would have to get 84% to get an A in this course. Here's another example about quality control in business, and this is an important application because in manufacturing you want to give exactly what the customer expects. If you give them less, they will be disappointed. If you give them more, you're losing money. So bottles of cola are to contain a volume with a mean of 591 millimeters, but some variation can be expected. So any body at or below the 20th percentile is rejected and has to be refilled. Suppose we know that a bottle that contains 593 milliliters of cola is at the 60th percentile. What is the smallest volume that will be accepted? So this is the 60th percentile. Now we are not given the standard deviation, but we can determine it from the given information. We want to find a z-value that corresponds to the percentile. So Appendix D shows that the area from 0 to 0.25 is 10%, which gives 0.6 when added to the 0.5 from the left half of the distribution. Thus, z equal 0.25 corresponds to the 60th percentile. We can then use the transformation to solve for sigma. So you see here is the 0.25, the z-score, that's 593 minus the mean 591 over sigma. So we solve for sigma. This is algebra, and you should be able to do this. We find that sigma is equal to 8. But now we can solve for the 20th percentile. From our table, we can calculate the desired x value. So Appendix D shows that the area from 0 to 0.84 is about 0.3. So by symmetry, the area from minus 0.84 to 0 is also about 0.3. Therefore, the area to the left of minus 0.84 is 20%. That's the 20th percentile. So we have that the z-value is minus 0.84 is equal to x, that's what we don't know, minus 591 over 8. And we're going to solve for x. We multiply both sides by 8 and add 591, and this is the answer. So we conclude that any bottle containing less than 584.3 milliliters of cola is rejected, and anything containing more than that is accepted. In the real world, there will be upper limits on this as well. Now, technology can be very useful in doing this, and every student at the College of DuPage is entitled, just by belonging to the College of DuPage, to get a free copy of Office 365. And this is free to College of DuPage students, but it has many statistical functions here. I'm not talking about the calculator because you'd have to spend $100 buying the calculator, and I'm not making anyone do that. This is free for you. But you see, we can use this to solve both problems. So here, and this function is called normal inverse in Excel. You can say, oh, I want to know what is the value that is associated with a probability of 75%. So here's the picture. It is a normal bell-shaped curve, but here is the area is 75%. And also I'm just using mean 0 and 1. You could actually put anything in there, and it will solve, and it will tell me that this number is 0.6745. So you see, this is one of the great problems. Given the probability, find x. We just did. The other thing is, given x, find the probability, that is normal.dis. And if we want to find, if we want to say, oh, if we're 1.96 standard deviations above the mean, what is this area? Well, there's 1.96, and the area from the graph is going to be 0.975. But here I plug in the x, mean, standard deviation, and I will do the calculation, and it gives me this number. So again, technology is something that can be used and is very powerful. And here is some free technology for you from the College of DuPage. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.